Vectors and dot products. We're going to start by finding the dot product of two vectors, and the dot product is just another operation that we can perform on vectors, much like we did with addition or scalar multiplication. The difference here is when we perform the dot product, our result is a scalar rather than a vector. So it's going to be an actual value that we sometimes will multiply by other vectors. To find the dot product, we're simply going to multiply components and then add the result of those products. So if I'm taking the dot product of u and v, I'm simply going to multiply the first two values together. I'm going to multiply the second two values together, then I'm going to add that. So let's just do some practice together. It's pretty straightforward mathematics. And if you're up for it, you can also find plenty of vector multiplication websites and so forth where you can just plug in the vectors and it will find the values for you. But again, pretty easy math. So if I'm finding the dot product of u and v, then I'm going to start with negative 2 times 4, which is negative 8, plus 3 times 0, which is 0. So I'm going to get negative 8 plus 0, which is negative 8. For uw, again, now I'm going to start with negative 2 times 2, so negative 4, plus 3 times negative 3, which is negative 9. Add those together to get negative 13. And finally, VW, I would start with 4 times 2, which is 8, and 0 times negative 3, which is 0, so 8 plus 0, which is 8. Now keep in mind that I just found 3 different dot products, but that doesn't mean I couldn't also find the dot product of u with itself, and I would do it the exact same way as I did any of the other questions we just went through. Let's look at a few properties of dot products. The first is the commutative property, which says the dot product in either order is still going to be the dot product. So it doesn't matter if it's u times v or v times u, you're going to get the same solution. The next is the distributive property. So u times v plus w is the same as u times v, u dot v with u dot w. If you have a scalar multiple, remember, this is a product, so please don't try to distribute the c, because again, we don't distribute when this is multiplication rather than addition. So here we're just saying you can either take c times u and then dot product with v, or you can take u times the dot product of cv, or you can find the dot product and then multiply by the scalar. So any of those things are going to result in the same solution. And then we have, if you have the 0 vector, which as you can guess is 0, 0, 0 is the 0 vector, which you might see look like this, or you might see a bold 0, which is what this is. I don't know if you can tell the difference between those two, but the 0 vector times any vector is 0. And then if you take a vector and dot product with itself, this is the notation that you're going to see. So you might see that in some of your formulas, or you might see it written like this. We're going to take a look at a few questions that we can use the dot properties to help us evaluate. So for instance, u dot v multiplied by w. Now I want to point out a difference here. Keep in mind that a dot product is going to result in a scalar, whereas this is a vector. So what we're going to do is we're going to end up with a scalar and we're going to multiply it by a vector. Now it's up to us if we want to do it in a different order. So obviously we can see that we could either take w times u and then find the scalar of w, u, and v, or take w times v, or we could go ahead and find the dot product. So I went ahead and found the dot product of u and v, which was negative 8. And then I took negative 8 times w, but again, I could have done that in another order and gotten the same result. The second one, we have u dot 2v. Again, I already know uv is negative 8. So if I know uv is negative 8, I can just rewrite this as 2 u dot v, which is 2 times negative 8, which is 16. So that's how I can save myself some work. Lastly, I have find u So again, remember that's the magnitude or distance. So that would be, if I take u squared, I'm going to take u times u, the u dot product with u, which gave me 13. So taking the square root of that would give me radical 13, which would be the magnitude of u. Let's take a look now at how to find the angle between two non-zero vectors. So there's two formats of our formula, and as we always have with any alternate forms of a formula, it's just someone doing the math work for you so that you can be a little lazier. If you had to memorize a formula, memorize this one, and then if you need to do the algebraic manipulation yourself, I'm sure that you wouldn't even break a sweat doing it. Obviously here they have just multiplied each side by the magnitude of u and the magnitude of v to isolate u times v. And that's all they did to get that alternate form. Now, why do they have an alternate form? Because if you're going to solve a question like number 1, you're going to use the first form. But if you have a question like number 2 where it says find u dot v, well then, of course, we're going to use the one where u dot v is already isolated. So let's take a look at our first question. We're finding an angle in radians between two vectors. Now, I always encourage you to try to visualize if you're able. So if I have vector 3, 2, that looks like this, and vector 4, 0 looks like this. So I'm trying to find theta. Now, we know if we're finding this in radians that this is 1 pi radians, or about 3.1415 and so forth radians. So it would make sense that my angle is going to be less than a radian. So always keep things like that in mind as you're working so that you can do a check at the end that it makes sense. So which format am I going to use? I'm going to use this format right here, which says take u dot v, that's 3 times 4 plus 2 times 0 in the numerator. In the denominator, remember, I'm just going to be taking 3 squared plus 2 squared and then the square root, and 4 squared plus 0 squared and then the square root. So that's going to give me 12 in the numerator, radical 13 times radical 16 in the denominator. This turns into 4, and then 12 and 4 can reduce to 1 and 3. So my solution is 3 divided by radical 13. But I'm not done with my question because the question didn't say find what cosine of theta is equal to. The question said find theta. So now we know that cosine of theta is equal to 3 divided by radical 13, or if you want to change it, you can into 3 radical 13 over 13. It doesn't make sense to do that because that's not my final form of my answer. I'm going to take the inverse theta of 3 divided by radical 13 to find 0.59 radians. So that does make sense in terms of the question. For question 2, we're finding the dot product, and here they're giving us theta is pi divided by 6, that the magnitude of u is 100 and the magnitude of v is 250. So very straightforward, just plug it straight in, 100 times 250 times cosine of pi over 6, which gives me 25,000 times radical 3 over 2, or 12,500 times radical 3. This brings us to probably the most important topic that you'll learn today, which is orthogonal vectors. So throughout your studies of mathematics, you're going to keep hearing orthogonal over and over and over and over. Whenever you hear the word orthogonal, I want you to think about perpendicular. Orthogonal vectors are simply vectors that form a 90-degree angle. So vectors u and v are orthogonal if and only if their dot product is equal to 0. So pretty straightforward to do the math here. We're just going to find the dot product of u and v. So 6 times negative 1/3, 10 times 1/5. That gives me negative 2 plus 2, which is 0. So the vectors are orthogonal. Again, I encourage you to visualize this. This is the vector 6, 10. This little guy down here is the vector negative 1/3, 1/5. Now, it's kind of difficult to tell, but these do form a 90-degree angle. Vector components. We just learned what an orthogonal vectors are, which of course are vectors that are perpendicular or form 90-degree angles with one another. Now, just like we did in our last section, section 6.3, we took component vectors and we rewrote them using standard unit vectors, and that took a vector and changed it into an equation which we could use in application problems. And that's kind of like what we're going to be doing here. What we're going to do is we're going to be able to rewrite a vector in terms of two other orthogonal vectors. So again, orthogonal means 90-degree angles that are perpendicular. So we're rewriting a vector in terms of two perpendicular other vectors. So W1 and W2 are orthogonal, and W1 is a scalar multiple of V. So what we have is we have my original vector, which here is 1, 3, and then we've got some other vector V. So that little guy is vector V. Now what we want to do is we want to think about V kind of as a line. So some scalar multiple of V. So it could be longer than V or shorter than V, but it's going to be along the same direction as V. And I'm saying, okay, I want to think about a light source right here that's shining perpendicular to this new white dotted line. And if I were to do that, what would that shadow look like? Well, I would end up with a shadow that kind of looks like this. And that is going to be our two orthogonal vectors. So again, if that light source is coming right from here, all on top, we're going to end up with a shadow here. And you can see that these two, I'm going to get rid of this white line and this green line. We can see that those two little vectors, 1, 2, will be orthogonal, 90 degrees, and will arrive me in the exact same place as 1, 3. So that's the idea about where we're going. Let's take a look now at the process now that we understand the big picture. So I've got vector u, which is 7, 6. I'm projecting 7, 6 onto 2, 1. So if you want, go ahead and graph 7, 6 and 2, 1 so that you have an idea. We're going to look at that together in a moment. Step 1 is to determine the projection W1, which means the first vector. That's the projection of u onto v, and that's how we're going to figure it out. So I'm going to take the dot product of u and v. So 7 squared plus 7 times 2 plus 6 times 1 over 2 times 2 plus 1 times 1. And then again times vector v, which is 2, 1. So 14 plus 6 divided by 4 plus 1 is 2 times 2, 1, which is 4 times 2, 1, which is 8, 4. So 8, 4 is the first part of my equation. So remember when we said we were going to rewrite u as W1 plus W2. So now I say u, which is 7, 6, is going to be 8, 4 plus whatever I find for W2. Now W2 is pretty easy to find because I know that if this is my unknown, I can take 7, 6 minus 8, 4 to find that unknown, which is negative 1, 2. So 7, 6 minus 8, 4 is negative 1, 2. And this is the way that I'm going to write that projection. Now, what does that look like? So here's my original vector, 7, 6. This little guy down here was v, 2, 1. And so I'm saying let's extend 2, 1 out as far as we need to. And so we're going to find that this guy is 8, 4. And then this guy is negative 1, 2, which you might say, okay, well that means negative 1, 2. So it's going to look something like this. Well, yes, you're absolutely right. But remember, parallelogram rule, when we are adding two vectors, we go to the end of the last vector and then go negative 1, 2. So that brings me to 7, 6. So that's the math that you need to do, is just those two steps, is to find W1 and W2. Go ahead and try this question on your own. I didn't change anything up except for the values of u and v, but it's the same process. So when you're ready, press play to see how you did. Again, my first step is to find the projection W1, so the projection of u onto v, which in this case is very, very small. So v is actually much larger than the projection of u onto v, which is 6/5, 2/5. Then I simply am going to subtract that from 3, -5 to find 9/5 and -27/5. And then I'm going to write my solution as two orthogonal vectors, so W1 plus W2. As I'm graphing this, again, u was 3, -5, so this guy down here is u, 3, -5. And v was this guy, and here, instead of extending v like we did last time, I'm actually taking a much smaller portion of v. So I'm saying 6/5, 2/5, which is right here. 6/5, 2/5. And then I'm adding to that the orthogonal vector, which gets me out to 3, -5. We're going to finish out with an application question about work. So here is a very poorly drawn truck for you to just amaze yourself at. So we have the work W done by a constant force F as its point of application moves along the vector PQ is given by work equals magnitude of force times distance. So stop for a moment. If we had the force going in the same direction as the object that is being pushed or pulled, this would be very easy to figure out. It would just be whatever the force is that is being applied on the object. What we have is not that simple. What we have is force going in a different direction as the object is being moved. So for instance, in this case, I have the force of an object that weighs 30,000 pounds. This force is -30,000 times j, j being the up and down direction, as opposed to I, which was right and left or horizontal. So I am going to be using work as either equal to the projection of PQ times the magnitude of the vector PQ, which is the distance, or work is equal to force times vector PQ. So let's take a look at how this works, because when you just look at an equation, it doesn't always make sense. So I have a truck with a gross weight of 30,000 pounds parked on a slope of 5 degrees. And I'm assuming that the only force to overcome is the force of gravity. That means I'm just looking at the -30,000 degrees. Oh, sorry, -30,000 pounds. Find the force required to keep the truck from rolling down the hill. I'm going to stop right there. That's all we're going to do at first. So the force required to keep the truck from rolling down the hill. Let's see what we know. I know that F is equal to -30,000 times J. And keep in mind that means 0I minus 30,000 J. And that just represents the force of the gravity pushing down on that truck. And then we have the unit vector along the hill. This is from our last section. We're taking cosine of 5 times I plus sine of 5 times J, 5 being that angle of elevation. So what am I going to do now? I'm going to find W1, which we're very familiar with. Now I want you to notice that I did go ahead and use cosine squared d plus sine squared d using this component vector. I should have had a 5 instead of a d, but you get the idea, sine of 5. But we know it's a unit vector, and so that value is going to turn into 1 either by the Pythagorean identity or because it's a unit vector. So that leaves us with 0 times cosine of 5, which cancels out, -30,000 times sine of 5, and then multiplied by v. That's going to give me -2,614.67 pounds. That's not the answer to question number 1. Question number 1 says, what's the force required to keep the truck from rolling down the hill? So this is the force going in this direction, right? This is the force, and I need to find I need to counteract that. So my answer to question 1 is that I need positive 2614.67 to cancel that out. So that's the force required to keep the truck from rolling down the hill. Question 2 says find the force perpendicular to the hill. And perpendicular to the hill would be using the distance formula. So we're taking 30,000 squared minus 2614.67 squared, and then to find that this is the force required, or this is the force perpendicular to the hill. Coming up next, we have the complex plane.